we have looked at two models for computing devices so far in this course. And these two models were finite automata and push-down automata. Finite automata, they were good for devices that have got small amount of memory. And this were able to take care of us in terms of things that are called regular languages. In fact, they were equivalent to things that could be expressed in terms of regular expressions. The other type of devices or models for computing devices we show was push-down automata. And these were good for devices with unlimited memory that's usable in the form of a last in, first out. That LIFO there is last in, first out, or in stack manner. And we saw why we needed them. These were for context-free languages where we needed something to remember that finite automata were not able to do. So there was access to memory we got, but that one was different in structure and was external. It was not something that was around the inputs. And with these two machines, what we have seen is there is quite a bit of things that we can do, recognize language and some tasks that we can do, but they were not powerful enough like we know computers today. And what the rest of the semester has for us is to look at models that are of similar spirit, but we want them to serve as models for general purpose computers, including the ones that we're using now to Zoom, including the ones that you're using now to do everything that you do in your courses. Would there be a machine like that that would be good? And the answer is yes. And with that class of machines, that model is called Turing machines. And these are named after the person who proposed them, and that's Alan Turing in 1936. And I think about 10 years ago, I think it was his 100th birth year. And so there was some celebrations. There are a number of things around computer science that are attached to this name. But whenever you see Turing machine, remember that it is named after a person called Alan Turing. And so these are machines, these are models. They are similar to finite automata, but they have unlimited and unrestricted memory. And they can do everything that a real computer can do. And so it is one of the ways in which we have been able to, or our field, computer science, has been able to abstract away things that real computers have with all their sophisticated things and all the details, what they boil down to, if we were to think of them as the most fundamental things that would still be doing computing. And so they are powerful, and that statement that they can do everything that a real computer can do stands true to this day, and they are. So in that sense, they could be used as surrogates for us to see what can computers do. And there are problems, and we will learn about them, that just like finite automata and push-down automata failed us to do sophisticated things, and we blamed it on the machines and we say they were not powerful enough. Here we have the most powerful ones and the ones that would do everything that a real computer can do. But there are problems that even such machines, such models will not be able to solve. And so that would give us a way now to say what is possible, theoretically speaking, to be computed. What is it that we cannot do? And that will be the problems that we have named for, and we have a way to reason why they are not going to be done by a computer. It will not become a question of speed. It's not going to be a question of architecture. It's not going to be a question of memory. It is going just to be a question of what is theoretically possible to compute. And so there are problems for which Turing machines cannot solve, and we will study about them. I'm going to rely on a schematic view of Turing machine before we get to the details of them and define them formally and so on. And so this is a nice cartoon, and this is a picture I took from the book, but this is a good way to think about what Turing machines are. And so it has got a control. Think of this as I have alluded to. These are some advanced forms of machines, and we have try to compare them with finite automata. So there is this notion of having to worry about how your states are, how you are going to transition and things like that. And so think of that control as a place where all of this is happening. If you want to think of it like what a computer would do, it will be more like a control unit, more like what the management of all of the architecture would happen. And so that's the control. And we have a separate thing called tape, and this is where the input would reside, and this will be infinite in size. So the memory of it is unlimited. And so we've got the control, we've got the tape, and then we've got a way to get from the control to the tape. We have a way to work with it, and that's called the tape head for that machine. And it will be able to both read and write symbols as it moves around the tape. And now we have already begun to see how this is different from finite automata, and I'm going to come back and spell those differences out in a second, but there is a difference in the sense that we are working with this tape that is infinite in size, and we are able to both read and write symbols onto it. So initially, the tape contains only the input stream, and it is blank everywhere else. And so that symbol that you see looks like a cup that is unfilled, or a U-shaped thing, that is a blank. That's a symbol, a special symbol we're using here. And the dotted or that rigged line at the end here that you see is to show that this is unlimited. Okay, so I'm going to continue talking about this one. So initially the tape contains only the input, and it stores information by writing on the tape. So this machine, that the Turing machine we have, is able to store information on the tape by writing on it, which is unlike what the other machines we have learned so far. Finite automata, for example, cannot do. They don't write, they just read. To read information, the machine can move its head back over the input, and we will learn that it would actually be able to read both going in both directions on the tape, to the left and the right. And it would accept or reject, and it will have an accept and reject with designated states. If you remember, finite automata, they would have an input, and they would follow their transition function and then arrive at an accepting state in which we say it will. If not, then we would say it is reject. There was no specific designated state called reject. In this case, we have. And if it doesn't accept or reject, we have this unusual situation, unlike other machines we've seen so far, in which it runs forever. So it may accept or reject, or it may run forever. And this is a good schematic way to look at what the Turing machine is. And so, as I told you, there is a difference between finite automata and Turing machines, and I'm going to summarize them. The first thing is that a Turing machine can both write on the tape and read from it. And the write part is novel, or is new, whereas in the machines we have seen so far, it was just about reading, consuming the input. The read-write head of the Turing machine can move both to the left and to the right, and this gives it power. And now you've probably started to see a glimpse of why Turing machine is a more powerful model than we have seen so far, as powerful as to say it can do everything that a real computer can do. So when it is boiled down to its basics, this is where the power is coming from, because it can store information on the tape. It's unbounded. It can go for as long as it read, and then one has the right to the ability to move in both directions, and therefore you can. It may take you time, and I would not recommend that you try to implement a Turing machine and do something, a startup of your own. You will not be successful in that one. It will be very, 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 very slow. But if you wanted to boil it down, it would come to having this flexibility. So it can go both left and right. The tape is infinite, and that's not realistic, but it will give us a theoretical foundation for having to say when it is possible to compute or not. And so the tape is infinite. The fourth one is the special states for rejecting and accepting, which are called accept and reject states. They take effect immediately. You probably don't see any context so far from what I have told you to appreciate this point, but this is what it means. In a finite state automata we have seen so far, we would read the entire input, and that's only then we would say whether it's accepted or not. In this case, in Turing machines, if we reach an accepted state, we may not bother to read the rest of the input. And you will see, as this discussion continues, that Turing machines come closer to how we think about programming, how we think about algorithms. And so you have plenty of examples from your own experiences where you have a program and it has found the solution, so you don't want to continue anymore. You don't have to even have a need for having to read the rest of it. So by the same token, when this special states of accept and reject would take effect immediately. The moment that they are reached, we don't have to expect for the rest of the input to be read for the Turing machine to arrive at one of these two states. All right, I'm going to use an example to informally describe a Turing machine. And by the end of our discussion today, we will formally define a Turing machine, much like what we have done with the models we have seen so far. So the example I would use will be, this is language. And this language is going to be a string separated by hash symbol, and to its left and to its right, it has got the same copy. And so we have got W on the left and W on the right, and this is a binary input. The alphabet is 0 and 1, and it could be repeated as many times as possible, but the language is such that you have something, hash symbol, something, and those two somethings are exactly the same. Then we want to design a Turing machine that would accept if the input is a member of this one, and it would reject it otherwise. This is online. I'm not sure how much I could get a good participation from you, but I would like to ask this question. If this was a question given to you, how do you think you would go about it? Designing a Turing machine that would recognize this one. Given an input, it would tell whether it's a member of this language or not. How would you go about it? Somebody unmute and tell me. That would be fantastic. If not, somebody could just jot down a quick one on chat. I'll give you 30 seconds to act one way or another, and then we'll start actually discussing how this could go about. Any volunteer for 30 seconds? Within 30 seconds, you could tell me how to go about this one. I'm not going to blame anybody if you don't volunteer, it's okay. For future classes, every time I ask, I would like to have participation. So try to, even, I know some of you know the answer, so you've got something to say, but you may feel like not doing it, but please do so. But I think some of you would probably have a guess on how we might want to go about this one. So the goal is here, we've got this input that's coming, and we want to make sure that it is the same to the left and to the right. So somebody is saying, write W from left to right until reading a hashtag, then read it back if it's identical accept. So there is an elegant solution somebody has suggested, and that was the case. And so this sounds like how you would go about it if you were to write a program for it. So case suggestion is read W, the input, from left to right until you get the hash symbol, and then read it back. And if it is identical, accept, otherwise ignore. That sounds like you have something that you're looking for in terms of W itself. And that's not exactly what we want, but the idea is there. So you've got the idea right in terms of having to use that demarker, the hash symbol, and to see that things are the same on both left and right. All I'm going to suggest a solution, and we're going to talk about the Turing machine, but I'm going to give you a caveat right now. So Turing machines are not going to be the machines that you would be working for in terms of efficiency, as solving the problem or not is the more important thing. And there are problems when we will talk about complexity where it will help us to see whether things would belong to one class or another class. But in terms of having to be efficient is not a prime objective, because the Turing machine itself is not meant to make things in an effective way or anything like that. In fact, it is not. And there are some theoretical results. So what I'm going to tell you now is how you would actually successfully solve this one. And you may get clever, and sometimes you may find some other, for lack of a better word, I would call it optimization, in which you could do your computation more efficiently. But even on a Turing machine, to try to be efficient would be helpful in algorithm design. We'll see examples of that kind. So what I'm going to tell you now will be a correct way to solve it, not necessarily the smartest way. And so here's how it's going to go. We are, and so Casey is right. So there is something that would compel us to look for how to take advantage of the separator symbol, the hash symbol here. So the idea, the strategy we'll employ would be to zigzag. We'll be zigzagging to see, because we don't want necessarily to spend a whole lot of time when we know that these things are not the same. And the first time we would discover things are not the same is by looking at what would happen if I see the very first element on when I am things onto the left of the hash symbol and the first element to the right of the hash symbol. If those two are not the same, I don't even need to worry about the rest of it. And so I have to actually systematically go through this and proceed only if they have a motivation, a reason for having to proceed. So we're going to zigzag and we're going to remember. We're going to remember what we have seen so far, whether they match up or not. And so we'll zigzag to the corresponding places on the two sides of the symbol and determine whether they match. And we are going to have a way now to show that we have seen something. And that is where the power of the Turing machine would come, because we can interact with the tape by writing on it. And so we can go and say, here was the input, we have read it. And so I mark, or we mark how that we have read it by putting something on it. And we'll see that we'll actually put a cross on top of the thing that we are reading. But remember what I'm going to continue to explain now. We will not need to proceed if we find the first time they disagree. And so first check. If they pass, then I will go to the next one and so on. And for that reason, I'm going to be zigzagging. So we're going to design our machine, and we'll call this machine M1 as our Turing machine to work in this fashion by zigzagging. So we are going to have to do multiple passes over the input to string. And this is the place where we are allowed. We are allowed to have multiple passes over the input. We are allowed to go left and right on the tape. We are allowed to write things on the tape if we have information to store. So we're going to make multiple passes. And on each pass, we are going to have one of the characters on each side of the symbol matched up or compared. And to keep track of things that we have matched up, we're going to cross off. And we're going to cross off literally by having to put an X mark on the input that we have read. And so if the crosses are all, if we have crossed off all symbols, that means everything has matched up successfully. And so we could go and declare victory, and M1 goes to accept the state. If it discovers a mismatch, it enters a reject state. That's the informal description of how this Turing machine would work. CptS has a nice way to describe algorithms for Turing machines. And I've quoted from the book word for word how this machine's algorithm would be written down. We will, when we get to, and I'm going to watch my time, 10:45 is what the time is now, we have 15 minutes, and I want to finish this discussion today by having a formal description of what a Turing machine is. And so we will come to a point when we look at examples of Turing machines where we would go describe them as we have done with finite machine, state machine, or FAs and DFAs and NFAs. And so in that case, we were doing things at a very lower level. We can do with Turing machines that type of description, and we will see at least a couple examples, but that's not very helpful. And in fact, it becomes very, very, very tedious, and it kind of obscures what we want to achieve from having to see what Turing machines can do. A much better thing that CptS argues for and successfully does so is to describe them in the form of a pseudocode. And this comes very close to how you would write your programs. And so the description will be more like in English, but there will be enough of a detail to say, and it will be a specification when you would say things are accepted and when things are rejected. And so here is the algorithm for it. And as you can see, it is put in quotation marks. And so we've got the input string W. So the first step will be to zigzag across the tape to corresponding positions on either side of the special symbol to check whether the inner positions contain the same symbol, the first two symbols. And then when we're done with that one, the next two symbols, and when we're done with the third symbol, and so on. If they don't match up, or when we do this, when we were trying to read, we never found this symbol that is supposed to separate them, then we have good reason to reject, and so we go ahead and reject. Otherwise, we cross off the symbols, they are checked to keep track of which symbols correspond. That will be step number one. Step number two, when all symbols to the left of the hash symbol have been crossed off, and this is what Case's answer was alluding to, when they have been all crossed off, check for any remaining symbols to the right of the hash symbol. Remember how we were crossing off. We were crossing off things when they matched up. We found match, bingo, so we put a cross. We found match, bingo, we put another cross. We were doing this. And so by the time we have crossed off things, if there is anything that, then with this, we were dictated by having the symbol to the left of the hash symbol. If there is anything now left to the right, that means there is something more. In fact, it probably was longer. That string was even longer in size. And therefore, there is no reason that they will be equal and we can reject. Otherwise, if they have been crossed off, and if they are of equal size, then we would accept. This will be a complete description of the algorithm that doesn't go to the level of saying how state transitions and things like that are happening. It is described in a high level, and it is enough of an algorithmic description. I've got a picture, and I'm not going to spend a lot of time on looking at it now, but when you get a chance, you can take a look at what this means. This is a particular kind of input, and this input actually is a place where the Turing machine would accept it. And you can see that the thing to the left of the hash symbol and to the right of the hash symbol are the same. You just see now the tape head progressing. And so when the crosses are made and when it is crossed off at the end. This is not all of it. This is just a snapshot, and some of them are skipped over, but you get the idea of having to go to zigzag and making sure that the corresponding entries of the two sides of the hash symbol have matched up. That was a snapshot. All right, so we're going to do now a formal definition of a Turing machine, because we have said that this is much like a finite automata, a machine. We are going to have a tuple, and our next slide is going to define what the contents of that tuple would be. But the most important part, or the central part, is the transition function. And so I have written out what the transition function would look like. And you may remember from our discussions on NFAs and DFAs, what the transition function is going to take. It's going to take us from one state and some set of conditions to another state. And in our case, we have states, and Q will be our term to use the set of states. But it's not just the state that matter, but what the status of the tape. And so the tau there, it's supposed to be a tau, is the tape alphabet. And I'll come back and tell you what the difference between that one and the input alphabet is. But you already know because when we were matching up these strings now, and 0 and 1 was what the input alphabet was, we were crossing off. And so we were actually using that mark cross off as one thing to read. And therefore, we needed something other than the input to be able to make our determination. Therefore, that tau, the tape alphabet, is going to be the one that will help us define the transition function. So state and the tape's status, the tape's content, is going to determine where we are, and where we are going to go will be another state and another condition on the tape, whether what we have done on it, and this new thing, L and R. And that is to mean the head of the tape has gone to the left or to the right. L stands for L, left, and R for right. So when the machine is in a certain state Q and the head is over a tape square is what Sipser calls it. You can also call it a cell containing a symbol A. And if we have the transition function that says delta of QA is R, B, L, what we mean is we are going to write the symbol B that's on the new position, replacing A, what we have read, and we go to a new state called R. So Q to R. And the L and capital R indicate whether the head moves to the left or to the right after writing. All right, so now we can formally define it. And so surprise, surprise, we've got another machine now, we've got tuple. And so this time they become 7 of them. And so we've got Q, sigma, tau, delta, Q0, Q accept, and Q reject. And so Q is the set of states. Sigma is the input alphabet. And the input alphabet can be anything, but we want to reserve one special symbol to make sure to indicate that we have come to the end of it. And that's the empty symbol. And as I have shown you before, we're going to use this symbol like a cup, an empty cup, to show that it is at the end. Tau is a tape alphabet. And this one has got the blank space that shows us what the end of it is. And the input alphabet is also part of the tau. So the tape alphabet has got, of course, it should contain the input alphabet, but it has got this special symbol. Plus, it could have something else, like the cross we showed you. when we had 0 and 1, our sigma, the cross to mark off things that we have read, was a special symbol used. We could write more things. And so in general, tau will be something, a superset of sigma. So the transition function, as I explained, will take us from states and the tape alphabet to state, the tape alphabet, and left and right. And that will be our transition function. If you're curious, right now, you can see whether you would kind of make this one similar to an NFA or a DFA. And it looks like this one is deterministic because it's just having one way to do. So for a given state and a given tape alphabet that we have read and a symbol that we've read, we'll go to a particular state, do a particular thing on the tape, and then move to the left or the right. Not more options like what an NFA would do. So this is a deterministic behavior. Later in the course, we will learn that it actually doesn't even matter whether this one is deterministic or non-deterministic. But it is, in the way it is written now, it is deterministic. And so the other things are the states. So the special ones, the start state and the accept and the reject states. They are all members of Q. And we have got this final condition that we would insist that the reject and the accept states are different. And they are distinguished because they would help us come to different conclusions. Let me see. Okay, somebody asked a question and then somebody else answered it. So I'm going to continue. So this is going to be a little technical. Any questions so far? And I'm going to interpret silence means like we're all on board and we have had enough coffee and we're doing fine. That's how I would interpret it. Okay, if there is any different interpretation I should take, let me know on the chat side. I'm going to keep my eye on. So we've seen formally how NFAs and DFAs would do computation, and we're going to do something similar for Turing machines. And then it could get a little boring, and sometimes I'll just make them so that we have some formal ways of saying them. But initially, the machine receives the input, and it's a string, and it has got length n. That's what this one says. So the input string is sigma, and so I'm going an asterisk on it to show that I can have repeated elements of it. And so we've got the leftmost n squares of the tape are occupied by this one. So we don't want to start our tape somewhere random. We want to use the input of the tape using the leftmost n part of it for the actual input, and then the rest of it will be blank. And we know that this thing is infinite and it goes to forever. So the head starts at the leftmost square of the tape. That will be how things would start. And as the computation proceeds now, according to the rules that are specified by the transition function, and as we do this, we may come to a situation where our machine tries to move its head to the left and tries to fall off the cliff. And we want to prevent that. And so we have our transition function telling us, do this, do that, go to the left, go to the right, and then it brings us to the left end of the tape, but still wants us to move to the left. And we're going to be very careful with our machine, and we don't want it to die of falling off the cliff. And so we'll say, no, we're not going to respect your transition function, I'm sorry. So even though it's saying something, we'll just leave it there. And so that will be one thing how one of the computations will do. And this computation continues until it enters either an accept or a reject state. And if that happens, then we say the Turing machine holds. But this is not the only way things would turn out to be for a Turing machine. It could be just going forever. It never has reached an accept state, or it never reached a reject state. There is technical reasons why this would happen, and we're going to actually give a name for things like this, but it can happen. So it could go forever. So from what I told you now, remember what we're trying to do. We're going to try to do a formal way to describe how computation happens on a Turing machine. And so we've just kind of went through how computation does. And so we need a name for having to say what this transition function actually is doing. So it is taking from one thing that's called a configuration of a Turing machine to another configuration. So a configuration of a Turing machine is what the current state is, what the current content of the tape is, and what the current location of the head is. This completely or fully describes what the Turing machine's status is. And that's called a configuration of a Turing machine. And so we are now going to be going to define what computation means on a Turing machine by seeing how it goes from one configuration to another configuration. All three of these things are important. When one of them, more of them is missing, then we don't have a complete description of a Turing machine for that status. What I mean by complete description, of course, the complete description would require us having the full 7 tuples. That's not what I meant. What I meant was the status of it, how it is at the moment, is what a configuration means. And so it is represented for the sake of notation in some special way. And so I'm going to tell you how that one is written. So for a state Q and 2 strings U and V, notice U and V are not symbols, they are strings, so they could have multiple symbols in them. Over the tape alphabet tau, we write U, Q, V for a configuration, and Q is a state, U and V are strings, to mean that the current state is Q. The current tape contains UV, that's the entire content of the tape now, and U and V are separated now by Q. And the current head location is the first symbol in V. So remember what U and V were, they were strings. So the first symbol in V is where the current head is. So try to picture the picture I showed you before, where there was schematic. Instead of writing all of that, we could have this mathematical way to write it. U, Q, V. Q is a state, U and V are to the left and the right of the tape in a way, and the tape is right at the first symbol of V. And so the tape contains, otherwise, after the last symbol of V is all blank. And so this is how it looks like. And in fact, I have a picture. And so I've got here a concrete example where the input is, or the configuration is that string 1011, and then we've got state Q7, and then we've got 0111 after the tape's head. And so this will be called a configuration. We've seen an example. And so we will now try to say, much like state machines, and I've got only a minute or so left, and so I'm going to probably go a little bit faster on this one. We say a configuration C1, it yields another configuration C2 if the Turing machine can legally go from configuration 1 to configuration 2 in a single state. And so I have some notations for what is allowed in, or in this particular case, a concrete example of what is in the input alphabet or the tape alphabet, and some things around U and V. And we've got 2 states, QI and QV. And I'm going to show you 2 things when there is a left move and a right move. And so we've got this now, UA, QI, BV, and then the other one on the right are 2 configurations. You can see how they are 2 configurations by having to see what is to the left of QI and to the right of QI on the first expression, and to the left of QJ and to the right of QJ on the right one. And so we can see now, depending on whether we're going to the left or to the right, what would happen as one configuration yields another configuration. And this is just a matter of looking at them, and you would convince yourself what is happening, what the transition function is dictating us to do, and what is happening as a result of these translations. So it has become 11. I've got a couple of slides. I'm going to put up the recording of this one on Oswald immediately when I get it. But in addition to that one, I'm going to have this habit of having the slides themselves posted, just like as I used to do before. If I have slides, if I have handwritten things, I will do the same thing. But because it's 11 and we are, I know that some of you may have classes, I'm going to stop here and rely on you on looking up the rest of the slides, but we'll pick up from where I have stopped next time. Any questions before I stop? I might have failed to see questions when they were coming on the chat. I'm going to do a better job next time, and I see this. But we can continue conversations on Oswald also. Sometimes if I find something that I need to say more, I will drop a note there. So watch out for the survey that I will ask you. Complete it. If you have anything to especially tell me about how you're transitioning, I would love to hear from you. Please let me know. Otherwise, I will see you on Wednesday.